Here we are once again at the physics video lecture, psci 168, video lecture 30. Moving right along. Okay, so we're working on the heat engine and the efficiency of the heat engine, and this is going to be a little technical again. We started it last time, but it's worth it. Okay, it's going to be a great result, and after that we're going into all kinds of other interesting stuff. So yeah, let's do the heat engine and its efficiency, and I'll set it up again, and we're in no hurry. So heat engines and efficiency. So I'll remind us of what types of heat engines we have. And once we have this discussion mastered, we'll actually bring other natural processes into play that are can also be considered to be heat engines. But for the moment, we have the steam engine, we have the Crispus pyramid, which was airflow and a turbine. So I'll just write turbine. And you guys are supposed to go out and get all manner of interesting images of these things, because there's just a whole wealth of versions of this. But after that, we come to the schematic diagram. And this is something I want you guys to recognize and know. And if you look this up, you'll see that it's a very standard sketch of the process. And that was this picture here, in which we have a high temperature reservoir that gives off heat to an engine, and the engine does some work for us. Okay, that after all was the whole goal of the operation. We wanted to just burn fuel, for example, and get work out of it. But in analyzing the heat engines, we saw that you're only going to get a complete cycle if you give off some heat as well. Okay. And then we have this low temperature reservoir, TC. Okay, so this is the high temperature reservoir. And this is the low temperature reservoir. But for the moment, we can remind ourselves we're taking heat, taking thermal energy at some temperature, higher temperature, and we're extracting work from it, and there has to be exhaust. There has to be some waste heat, so to speak. So yeah, this is sometimes referred to as waste heat. Okay. But it's a natural part of the process, and it's a necessary part of the process. Yeah. So all of the heat engines that we've seen and other ones that are on the way can be brought into this schema. That's the idea. And the main thing is that there has to be, or an essential point is there has to be a temperature difference. Okay. Good. So that is, here, love numbering things. So that's the third point. And the fourth point is then the definition of efficiency. Namely, how much work can we get out of a given amount of fuel? So the efficiency definition that's above all the subsequent ones is that it's just the work that you obtained divided by the amount of energy that you put in. And these are both, say, in joules over joules, so it's a dimensionless number, and it has to be less than or equal to 1. Okay, so far so good. I then define the ideal engine, and this is already, in essence, the ideal engine, but I'll be more explicit about it. The ideal engine has no heat flows other than these that have been listed here. So there's, and no energy quanta other than the ones that have been mentioned here. So there isn't some extra energy being lost to friction, or there isn't some extra energy just being radiated off. So it's the ideal engine. So I'll just write no friction, etc. No friction or other losses. No friction and no other losses. Because remember, the waste heat is a necessary part of it. It's just the exhaust. Okay. Or it should be the exhaust. So in that case, we have two laws. We have energy conservation, right, which we've been learning about all semester, energy conservation, and in this scenario, QH is equal to W plus QC. Okay, from that energy in, you're either getting work or you're having waste heat, and that's it. And out of this, we had the ideal efficiency. I just brought W divided by QH. Okay. And then I ended with a 1 minus QC over QH. Okay, that's very simple, just dividing through. Okay. So the W was QH minus QC. I divided by QH and I obtained this. So we had that last time. That's no problem. Clearly less than 1 because we're subtracting something off. And now I'm at the point that I left off last time. I want to get the maximum possible efficiency. And the way I'm going to do it is use the second law. So energy conservation, as you guys remember, this is the first law of thermodynamics. So maximum possible efficiency. And what we're going to use is the second law. Using the second law. Yeah, it's supposed to say using. Okay. U-S-I-N-G. Second law of thermodynamics. Second law of thermodynamics. That's the E. Second law of thermodynamics. Okay. And I have everything up here that I need, so I'm just going to analyze this picture using the second law of thermodynamics. So recall, we had delta S total is greater than or equal to 0, and this was equivalent to energy flowing from hot to cold. That was so the second law of thermodynamics, which I'm about to put the technical expressions back in, was equivalent to energy flowing from hot to cold. And of course we have energy flowing from hot to cold in this device here, in this heat engine. So here's what we have. We have delta S total. I'm going to write it out in a couple of steps. I'll leave enough room here. So delta S total for this process, okay, it's going to be minus QH over TH for the upper part. So for the energy leaving the high temperature reservoir, okay, energy is leaving, so minus QH over TH. And by the way, these delta Q's, these Q's are all positive in and of themselves. So put the minus sign in front. And then I'm going to write plus 0 because it's an ideal engine. It's just cycling. After one cycle, it's where it started. No friction, no wear and tear, so there's no change in entropy of the engine itself. The only heat flow, and I'll go ahead and label these, the only heat flow is then plus the QC over TC, because now heat is going to the low temperature reservoir, going into, and therefore it gets the plus sign. So yeah, you have to remember that discussion we had of the entropy and the rules for energy, but it was really just the rules for energy flowing from hot to cold. Okay, that's all it was. Okay, should I label this here? Zero change of entropy because it's an ideal engine. Here we have energy leaving, right? QH leaving the high temperature reservoir. And over here we have QH entering the low temperature reservoir. Oh, QC. QC into the low temp reservoir. Okay. So that's our delta S total. And we know that this is always greater than or equal to 0 because that's simply what this means here. Okay. Okay, I need more board, but having written this down, I'll just leave myself a little space. QH leaving, QH entering. Okay. So what we're going to do now is look at this inequality, the second half here. We know that this sum, with the 0 over 0, right? These two quantities are greater than or equal to 0. Therefore, we can get a relation here. We have QC over TC. I'm just going to add this one to the right side. Is greater than or equal to QH over TH. Okay, so that's the inequality that comes from here. And one more step. I have QC divided by QH is greater than or equal to TC divided by TH. So yeah, those are just cross multiplications. All of these numbers are positive quantities, so nothing can go wrong. Okay, remember, these are Kelvin degrees. These are kelvins. Okay, this is the result we were looking for, and we're going to plug it into here. So let's go ahead and sum this up. Am I still numbering? 5, 6, yeah, why not? 7. So now I should just be able to put this in right here. Okay. So now we have this E ideal, I'm going to call it. Well, it's equal to this up here. So it's going to be less than or equal to 1 minus TC over TH. That's a C there. Yeah, let's fix that. TC over TH. Because QC over QH is greater than, so I'm subtracting off a number. So this E ideal is going to be less than or equal to 1 minus TC over TH. So this ingredient is going into 1 minus TC over TH. And this is the amazing result that we're getting at, because, too bad I erased that picture, But yeah, for any heat engine, the maximum possible efficiency depends on the temperature at which you run it and at which it's exhausted at. Okay. And this result is as good as these two laws of thermodynamics. Okay, it's absolutely rigorous. So let me define something now. Define what's called the Carnot efficiency. Carnot was the French engineer who came up with this idea for the first time. So the Carnot efficiency is just defined as 1 minus Tc over Th. These two temperatures are well defined in terms of the heat engine. Put a box around that one. So that gets a little subscript C. So E sub C for Carnot temps in Kelvin. Very important. Okay. Yeah, and you know, with this definition here, I'm going to go ahead and rewrite it, and then we'll discuss this and see what it means. We'll do a couple numerical examples. In fact, I'll have you guys, I'll set them up, I'll have you guys calculate them out and make sure you have room for them in your notes. Good. So from the definition I just erased, remember we had efficiency is work over QH. That's very general, always true. So what we can write is the work we get out is at most the efficiency times QH. Okay. So if it's say 50% efficient, then you know we put in 1,000 and we get 100 and we get 500 out. That's the idea. Okay. The efficiency. So this is how much energy was in whatever you're burning for now. I'm talking about burning things. And this is how many joules of work we got out. So that's why you see how important the efficiency is. We want this to be as high as possible, but it's limited by just the temperatures between which the engine operates. Okay, let's put that down in so many words. Let's see here. So this is the maximum possible efficiency of a heat engine based on the temperatures it's running between. If there were no temperature difference, if Tc and Th were equal, it would be 1 minus 1 is 0. Okay. But if Tc is much smaller than Th, then you know the efficiency can be larger. So what we have to do is some examples. But I'll put this as a note first of all. A very important one, exclamation points. This is the maximum possible efficiency of a heat engine. And it's based on energy flowing from hot to cold, so this cannot be violated. Okay? So maximum possible efficiency is given by the Carnot efficiency. That doesn't mean you can even achieve it with these temperatures, because then you have to be such a good engineer to avoid all those other losses. Right? Just because we said the ideal engine has no losses doesn't mean we can actually do that. Okay, so that's something that you have to work towards. Okay, and of course engineers are working towards that all the time. Good. So the maximum possible triple underline. Okay, there's just no way to get a higher efficiency than the Carnot efficiency would be asking for heat to flow in the wrong direction. Okay, it just cannot happen. So now let's give some examples. The first example is just the difference between room temperature and boiling water. Okay, so let's TH be 100 degrees Celsius, but remember, it has to be in Kelvin. So that would be 100 plus 273, so that's 373 Kelvin. And let's let Tc be room temperature, or some ambient temperature, 20 degrees Celsius, but again, it has to be Kelvin, and therefore that would be 293 Kelvin. So yeah, always remember this. Put that as a note here, just so you have it. T in Kelvin is equal to T degrees Celsius plus 273. Okay, so this is the homework. Homework. Calculate Carnot efficiency. What you're going to find is somewhere around 20%. Okay, 0.2 be 20%. And I'll give a second homework problem, because you're saying, well, 20% is not that efficient. Okay, so how can I get a higher efficiency? It's difficult to get the Tc to be low, because in fact the machine heats up and the Tc is actually going to be a lot hotter than the outdoor temperature, okay, because the machine itself is hot. So what one has to do is have very high temperatures, very large pH, and you have to have means of releasing as much heat as possible. Okay, let me go ahead and erase this. So I'm going to leave room in your notes. You guys have a calculator. You get these. You get the actual numbers. So the next example would be TH equals, let's just say we had 500 degrees Celsius. TC, it's not going to just be 20, TC is, say, 80 degrees Celsius. So what you want to do is convert these to Kelvin and then calculate Carnot efficiency. And put that in your notes as well. Homework, calculate E Carnot. And one thing you can do is, you've got 1 minus Tc over Th. You can get a common denominator and have Th minus Tc divided by Th. And the utility of this is the upper temperature is just the difference of these, okay? Regardless of Kelvin or Celsius, it's the difference. And therefore, it can be written as, in this case, 500 minus 80 would be 420, right? 420. And then the TH has to be converted to Kelvin, so it's 500 plus 273, so that'd be 773. Okay. And I can see just by looking at it, it's well, not bad. It's around a half. It's better than a half. Okay. So that would be fantastic for a heat engine. Very difficult to get them this hot. 40%, even 50% is huge. So those are some examples. Now, you'll notice that waste heat, even in this great example, there's still going to be considerable waste heat if you're really producing a lot of energy. And that waste heat has to be dealt with somehow. Okay, so we had the work is E times QH, okay? And what about the QC? Of course, the QC is just the QH minus the work. equals the QH minus EQH, which is M1 minus E. Okay. So obviously, if you have 50% efficiency, you'll have 1 minus half, also 50%. Okay. So yeah, these are just some relations you can use, and we should do one more problem. Let me check the time here. Yeah, we should set up one more homework problem, since I just did this one for you. And this will just be this. This is just to be a little more fun, right? So if E Carnot equals 40%, which is to say 0.4, and cold temperature is, we'll make it 20 degrees Celsius again. Remember, you got to go to Kelvin, but we'll write down 20 degrees Celsius. Find TH. So good. You can learn to operate with these things. No big deal. Very important to realize, though, that there is this waste heat, okay? And it's not because we're not trying, right? It's just part of the process. And for large-scale energy plants, 50% would be a fantastic efficiency. And so if there's a 1,000 megawatts power output to drive, a city or a municipality, then there's that many megawatts of waste heat that are just having to be dissipated into the atmosphere. Or dissipated into the ocean. Somehow they have to be drawn away. Okay, so from an engineering standpoint, if you have an energy source, something that's burnable, then you have to design a machine, with certain temperature characteristics, and then you'll be able to say the fraction of that energy source that will actually be able to be delivered to the consumer. Okay, so yeah, we have it roughly outlined. You'd be able to do this type of rudimentary calculation, just like we can calculate our hydropower potential without much trouble. Okay, good. So I wanted to talk about more heat engines. Let's see what time we've got going on here. Yeah. So I wanted to not just talk about more machines, but other processes in nature that count as heat engines. And the two that are most interesting are hurricanes and tornadoes. Okay. And since we have this whole analysis, we can actually pretty much analyze a hurricane or a tornado in the terms of what we've been doing here with our schematic diagram. And this is something you could get some good images for as well, I think. So hurricanes and tornadoes as heat engines. So let's start with a tornado. Tornado, or hurricane as a heat engine. So with the tornado, you've seen some dramatic pictures before, right? There's a whirlwind. It's usually filled with a lot of dust, and it's moving through, destroying things. It's an extremely high speed wind. Okay, it's a funnel cloud, and the nature of this funnel cloud, it actually spins up when two air masses come towards each other, and kind of a shear airflow occurs, and it literally just spins up a funnel, okay? A whirlwind, funnel. You can see little ones occasionally out in the desert and stuff. What we have there then is warm, moist air and cooler air. So up, all the way up into the stratosphere even, we have cooler air up above, warm, moist air below. So this is for our analysis. We've got the TH down here and the TC up here. And the funnel cloud, or the whirlwind, is a chimney of sorts. And I showed you the chimney effect. And the reason it's a chimney is because it separates the inside from the outside. Okay? If you throw something at a whirlwind like that, it'll be deflected off. Okay? So there is an inside and an outside. And that inside and outside terminates on the ground at the one point and way up in the higher in the atmosphere at the other. So you have a chimney, you have high temperature, lower temperature, and in fact, the fact that the air is moist means that it even carries more energy in the terms of latent heat. So what that does is it feeds. So the process, the updraft with the low temperature, feeds on. Okay, wind air coming in from here and here, going up that way. It feeds on that energy being released, and so it's self-supporting. As long as it has the warm, moist air source, if you go from the tornado to the hurricane, you probably, when you follow that year after year, it's always forming over the ocean and it ends over the land. Over the ocean is where the greater amount of warm, moist air is. Once it hits the land, it starts to decay and die away. But yeah, that is a heat engine. And in fact, some clever engineers have come up with the idea of anchoring a tornado in one place and then setting up turbines to extract the energy from a tornado that's anchored to one place. You know what? I'm going to write that down for you guys. You could research this. Maybe you could get some good images out of this too. The concept is called the atmospheric vortex engine. And I had looked at that some time ago. So I'm not sure if it's still present online. It should be. If you look at the atmospheric vortex engine and you read into it a bit, you'll see that it's an engineer who knows this heat engine stuff, and he even discusses the possible energy outputs in terms of these temperature differences and some other thermodynamic quantities as well. But it's recognizable from what I've told you that's the idea. Okay. You've got chimney effect, you've got high temperature, you've got low temperature. And this will allow us to segue pretty nicely. So finally, what is driving this heat engine? Okay, if the tornado and hurricanes are heat engines, what is driving them? And the answer is it's solar energy. Right? The warm, moist air over the ocean is actually warmed and evaporated due to solar energy. So, solar energy drives all weather phenomena. So I'll just write weather phenomena. In fact, we can say all weather phenomena. And that's where we'll leave it. So we may do a little bit more heat engine review, but we're moving on into solar energy next. I usually do solar after electricity, but I realized that we're just going to keep on the energy, thermal energy theme for a while longer. Eventually, we have to learn about electricity and magnetism because that's how energy is transported. Right? It's not enough just to have a bunch of tornadoes all over the place. We have to extract the energy. Good, but we'll leave it at that and see you guys next time.